Hello, everyone. Today, we're going to discuss something fundamental in the world of electronics and computing: transistors and logic gates such as NOT, and OR. Did you know that almost all modern electronic devices we use, like smartphones, computers, and even washing machines, wouldn't exist without transistors? A transistor is a small component, but its role is immense as an electronic switch that controls the flow of current. Transistor is a semiconductor component. It means it can be a conductor and can be an insulator. The basic function of a transistor is very simple, only as a switch. This switch has a very high speed. There are several types of transistors. The most common we find is bipolar junction transistor, or BJT. Then the second is field effect transistor, or FET. In this video, we will only discuss about BJT transistor. BJT transistor generally has three legs: base, collector, and emitter. This type of transistor is also divided into two categories, NPN and PNP. N here is negative and P is positive. So for NPN transistor, the base is positive, and for PNP, the base is negative. The use of NPN and PNP depends on the application applied. In NPN transistor, the current enters the base leg that controls the transistor, while in PNP, the control is the current coming out of the base leg. In NPN transistor, the collector leg is the leg that receives the current, then the emitter where the current comes out, and the base is the switch. If analogized, the base is our finger when we turn on the light with the switch. Because the transistor is a switch, the transistor is used for digital use. On is 1 and off is 0, and 1 are digital binary numbers. Therefore, as mentioned earlier, transistors are very influential components in the era of information and digital. Transistors can be made very small, and the combination of several transistors can be a very sophisticated device. CPU or processor on the computer or on our phone has billions of transistors in it, and the number of transistors in the CPU will continue to increase, and this means the transistor will be smaller in size. Transistors may not be as simple as resistors, diodes, or capacitors. Transistor is a component that can be applied very simply and can also be very complex.
Using these switches, our computers can store information. More and more sophisticated. Each switch stores a single bit of information, a 0 or a 1. But computers don't just store information, they process it, transforming inputs into outputs. That's where logic gates come in. Logic gates are the building blocks of computer circuits. They accept input and produce output according to a set of logical rules. One of the simplest logic gates is the NOT gate, represented graphically here. The NOT gate takes a single input, either a 0 or a 1, and inverts it, so that the output is the opposite of whatever the input is. If the input is a 1, then the NOT gate outputs a 0. If the input is a 0, then the NOT gate outputs a 1. To represent the logical rule this gate obeys, we can draw a truth table, which is just a way of writing down the rules for some logical formula. This table says that if the input is 0, then the output is 1, and if the input is 1, the output is 0. Often, though, our computers need to be able to perform calculations not just on a single bit of information, but on multiple bits of information. The AND gate, shown here for example, is a logic gate that takes 2 inputs instead of 1. Let's call these 2 inputs A and B. As the name might suggest, the AND gate will output a 1 when both A and B are 1s, but in all other cases, AND will output a 0. We can construct a truth table here too. This truth table is a bit bigger, since with 2 inputs there are more possibilities to consider. If A and B are 0, the output is 0. If A is 0 and B is 1, the output is 0. If A is 1 and B is 0, the output is still 0, and only when both A and B are 1s is the output a 1. The OR gate, meanwhile, is also a logic gate that takes 2 inputs. This gate outputs a 1 when A is a 1, or when B is a 1. So if both inputs are 0, the OR gate outputs a 0. But if either of the inputs is a 1, or both inputs are a 1, then the output of the OR gate is also going to be a 1. These logic gates on their own follow fairly simple rules, but they can combine with each other to form more complex calculations. Imagine what would happen if, for example, we took 2 inputs, passed them into an AND gate, and then passed that output into a NOT gate, what would happen? If both inputs are 0, the AND gate will output a 0, and the NOT will turn that 0 into a 1. If only one of the inputs is a 0, nothing changes. But if both inputs are 1, the AND gate will output a 1, and the NOT will turn that 1 into a 0. In other words, this circuit appears to do the opposite of whatever the AND gate on its own would do.